Hello everyone and welcome to Sky Scholar. For the last 3 episodes, the physics of planetary nebula have been reviewed and challenged. Today we will conclude this analysis by turning our attention to the ultraviolet spectrum of such objects. If one examines the ultraviolet spectra of planetary nebula, there are very unusual features in that simultaneous emission and what appears to be absorption lines are present for the same element at the same time. This is seen in this figure. Note the shape of the spectral lines for nitrogen 5, oxygen 5, carbon 4, helium 2, and nitrogen 4. When a spectral line in astrophysics assumes this strange shape, it is said to exhibit a P Cygni profile. In this spectrum, the lines for helium-2 and carbon-3 appear as normal emission lines. Now, why is it that one can observe a P Cygni line profile within the ultraviolet spectrum of a planetary nebula? In order to understand what is going on, let us begin by reviewing how astrophysics currently views the creation of a P Cygni profile for a spectral line. At the onset, it should be stated that the current explanation for P Cygni profiles in astrophysics represents a catastrophic failure in logic. If you are interested in pursuing spectroscopic questions on your own, here are 2 great online books that present the basic ideas relative to astrophysical spectra. These 2 references are a beginning and are well written. The only problem is that such references will entice you to adopt the accepted explanations even if these ideas do not really make any sense. The accepted explanations for the existence of P Cygni profiles represent a prime example. P Cygni profiles were first observed in the star of the same name and in current theory are said to be related to the expansion of a gaseous cloud around a star. P Cygni itself is a hypergiant luminous blue variable star in the constellation Cygnus and is one of the brightest stars in the galaxy. In order to account for the appearance of a P Cygni spectral profile, examine this figure. Astronomers claim that the emission portion of a P Cygni profile results from a dense stellar wind near the star which is expanding away from the observer. The emission is said to be slightly Doppler shifted to the red. Conversely, the blue shifted absorption portion is thought to arise from radiation which is passing through a rapidly expanding shell of material in the direction of the observer. Material located behind the star is not observed. Of course, this is conjecture because in the standard model there is no other feasible way to account for the presence of a P Cygni line profile. The problem relative to the UV spectrum of planetary nebula is that the P Cygni profiles originating from such objects simply cannot be accounted for by invoking radiation about a single star, which was the case for P Cygni itself. As a point of interest, inverse P Cygni profiles have also been observed. In current theory, inverse P Cygni profiles are explained through the contraction of a gaseous cloud, typically around T Tauri protostars which are said to be in the early stages of star formation. While astronomers claim that T Tauri stars are experiencing cloud contraction, it is interesting to note that in the year 2000, a massive flare eruption occurred from the XZ Tauri system, as can be seen in this animation. The XZ Tauri system is said to be comprised of 2 T Tauri stars. Yet if contraction of a gaseous cloud was really taking place, then why would one ever detect flare activity? Something clearly does not make sense in our understanding of T Tauri stars as well. In any event, inverse P Cygni profiles have also been observed in molecular clouds when sampling the spectra of molecules such as these, as one can learn in this reference. Again, in this case, the inverse P Cygni profiles have been linked to the gravitational collapse of a molecular cloud, a claim that should be disputed. The problem with the claim that P Cygni profiles or inverse P Cygni profiles represent either expanding or contracting envelopes of circumstellar material is best highlighted by the fact that some objects display profiles which are highly variable over the course of days or even hours. Here's an example of how the hydrogen beta line shape can vary over a 3-month period in a T Tauri star. The numbers under each frame represents Julian time. Next, have a look at this figure, which demonstrated changes in spectra in the hydrogen delta line of another T Tauri star. The signal to noise is not great, and that is because the time frame is only a matter of hours. Wow! Talk about rapid variability in the formation of an inverse P Cygni profile. Next, have a look at these two figures taken from a luminous blue variable, S Doradus. Once again, enormous temporal dependent changes in spectral lines are observed in this case. Finally, examine this figure, which displays changes in the helium-1 line in MWC 342. The authors write, helium-1, 6678 angstroms, shows day-to-day changes in its line profile. We observe pure absorption, pure emission, the P Cygni profile, and the inverse P Cygni profile in this line. There are time intervals where this line disappeared. Surely the complex behavior in all these figures cannot be properly accounted for by claiming changes in the behavior of a circumstellar envelope which is either expanding or collapsing. The timescales are simply too short and the spectra too complex to permit such simple conclusions. Now, astronomers naturally assume that if a negative signal is obtained in a spectrum, then it must arise from absorption, as was the case for the Fraunhofer lines treated in this video. In reality, I believe that the explanation for lines which appear to have absorptive features require much more prudent analysis when P Cygni profiles are involved. First, let us consider this spectrum from NGC 7027, concentrating on the solid line. Note once again how there are clear P Cygni signatures in these two regions in the ultraviolet. What about the rest of the spectrum? One can note a clear absorption feature here in the optical, close to the IR region. Yet all the other lines are obviously in emission, with no signs of P Cygni line profiles. This serves to immediately highlight that the current explanation for P Cygni profiles cannot be correct. One cannot simultaneously invoke that the expansion of a gaseous cloud alters some lines but not others in the same spectrum. For the current explanation to be true relative to an expanding cloud, all the lines must display P Cygni features, not just some of them. Clearly, the cause of P Cygni profiles has absolutely nothing to do with the current explanation with gaseous cloud expansions towards or away from the observer. Rather, it is much more likely that we are dealing with chemistry. First, consider a tantalizing idea. Imagine that within the P Cygni line profile, we are actually not dealing with absorptive and emissive features as currently believed, but rather with two simultaneous emissive features which are 180 degrees out of phase with one another. Now, how can this possibly occur? Recall in this video that condensation reactions in planetary nebula were proposed to account for all the emission lines. Returning to the most important case, namely the forbidden line from oxygen 3, it was easy to account for this line by invoking condensation reactions using water to deposit two negative hydrogen ions directly onto a condensed hydrogen structure, as seen in this reaction and figure. Following the transfer of the hydrogen atoms, the oxygen ion departs with one electron still in excited state. The condensation process is completed when a photon is emitted through a forbidden transition and the activated electron returns to a lower energy level. In this case, the excited oxygen ion was completely free from the influence of the condensed hydrogen structure when it emitted a photon. As a result, emission from such ions cannot be associated with any distinct phase because there is free rotation of the emitting species. However, consider what might happen when an atom or ion is still interacting with the condensed hydrogen structure when it seeks to emit a photon and return to a lower energy level. In that case, phase can enter into the problem. If you take an atom or ion and now allow it to interact even slightly with condensed matter at the time of emission, something fantastic can occur. When the atom is ready to emit, it will be influenced by its local environment, which can very slightly distort its electron cloud. Because free rotation is now restricted and a definite geometry exists relative to the electron cloud distribution, the emitted photons can adopt an absolute phase during emission. For the sake of simplicity, let us invoke two separate phases as shown here. Influenced by the local environment and the resulting distortion of its electron cloud, the emitting species will produce photons of different phases with fixed probability. Note in this figure that the wavy yellow line is depicting a photon emitted with a characteristic initial phase. Next, the blue wavy line is depicting the emission of a photon with a phase shift of 180 degrees relative to the first photon depicted in yellow. In this sense, the two photons are phase-locked relative to one another as a result of conditions prevailing during the emission. If the phases are separated by 180 degrees upon emission, then one emission line will be positive and the other will be negative when the spectrum is finally processed. Photons of different initial phases can be emitted at slightly different frequencies as a result of the ion-matter interaction taking place at the time of emission. That results in the P Cygni line profile, which we observe not only in Planetary Nebula, but also in P Cygni itself. The magnitude of the positive and negative emission components are governed by the probability that the emitting species has of emitting either one phase or the other while interacting with condensed matter. Everything now becomes governed by chemistry of the atoms involved and their specific interactions with this matter. This explains why only certain lines display P Cygni profiles in the spectrum, while the vast majority do not. But there is something more to extract from this analysis. Clearly, the current explanation for P Cygni line profiles cannot be reasonably adopted. Obviously, once again, not all spectral lines in this figure assume P Cygni profiles, but this should have been the case if the currently accepted explanations were correct. There is simply no other way to account for the presence of P Cygni profiles in the context of gaseous stars and planetary nebula, which are said to be comprised solely of gases. This represents a fatal blow for these models. Conversely, the argument now advanced is the only reasonable explanation for these observations. As such, this constitutes strong evidence that the objects which are emitting P Cygni or inverse P Cygni profiles are composed in part of condensed matter. In any event, different phases in spectral lines are common in certain nuclear magnetic resonance techniques, and now we can have similar phenomena in astrophysics with the P Cygni line profiles. Finally, let's take a moment to examine X-ray emissions in planetary nebula. This will bring home the point that emission lines in such objects must be locally produced. Relative to X-ray spectra from planetary nebula, here is a sample of the conjecture we hear. Planetary nebula, the progeny of low and intermediate mass stars, are formed by the interaction of the fast stellar wind from its central star, which is currently evolving towards the white dwarf phase, and the slow wind ejected in the late stages of the asymptotic giant branch. The strong interaction between these stellar winds causes a reverse shock to progress throughout the fast stellar wind, shock heating this tenuous wind up to X-ray emitting temperatures and producing a hot bubble. Wow, imagine, now we are going to get X-ray emitting temperatures in the millions of Kelvin in the outer regions of a planetary nebula. But the optical spectra demonstrate that the large extent of these objects only display temperatures of a few tens of thousands of Kelvin at most. So which is it? Tens of thousands of Kelvin or millions of Kelvin? Perhaps astronomers might decide to reconcile some of their wild claims. In any event, it is easy to demonstrate that such conjecture relative to stellar winds are false, not only by the presence of ions at low levels of ionizations throughout the nebula, but also by simply examining the X-ray images. Such images demonstrate that X-ray sources within planetary nebula are localized in many instances and simply cannot originate from the interaction of two stellar winds. In other words, once again, X-ray images demonstrate that emission lines from planetary nebula are produced by local conditions and have absolutely nothing to do with electrons or wind generated either by the central star or elsewhere in the object. We are seeing the effect of reactions with condensed matter at the local level and nothing more. X-ray emission images from Chandra easily make the point. In these images, X-rays are shown in purple, and optical emission from the Hubble Space Telescope are colored in red, green, and blue. One can readily observe that the X-ray emission is not symmetrical within these objects. We can remove the optical contribution from the Hubble to obtain these X-ray images. Next, in order to facilitate this analysis further, let us concentrate on the Cat's Eye Nebula. Here are the expanded side-by-side views of the optical and X-ray images for this nebula. Clearly, it is difficult to argue that the X-ray image is being somehow magically created by collisions of fast and slow solar winds. Convincing evidence is provided by this figure, which illustrates the relationship between the X-ray emission on the upper row, the optical image on the bottom left, and a composite overlay of the X-ray contours and the optical image on the lower right. Clearly, such an X-ray profile cannot be accounted for with fast and slow solar wind effects emanating from gaseous objects. Finally, here's a group of X-ray images from 4 planetary nebulae. It is evident that there are localized regions of emission which cannot be reconciled with the idea that these X-rays are originating from colliding fast and slow solar winds. The question now becomes, why do we have such extensive and dispersed X-ray emissions in planetary nebula? Surely this cannot come from the effect of a central star, nor can the astronomers try to argue that shock waves within the nebula are responsible. A simpler explanation, and one which is guided by our analysis of the solar corona, is that we are witnessing the result of chemical reactions involving the transfer of electrons, much like we learned in this video. We are witnessing a localized process and not one magically driven by colliding winds capable of generating the most elaborate of structures. Again, if the interactions of stellar winds were able to generate X-rays within planetary nebula, then all the ions should be extremely ionized, and we would not be able to easily detect species such as the forbidden lines from oxygen 3, for instance. The stellar wind idea simply does not make sense. Rather, we have to be able to account for X-ray production and the simultaneous presence of oxygen 3. The only way that this can be accomplished is by using differing chemical processes in the same localized region. That is all for today. I believe that the explanation relative to P Cygni profiles will come to reformulate a vast area of astrophysics. As a result, it is my hope that if you enjoyed the video, you will promote the channel, mention the videos to your friends and to your local astronomy club, support me with a like, and subscribe for more videos as we look more closely at the sun, the stars, and beyond. Scientific comments are always welcome down below, and I'll see you soon on the next video.